Hey everybody, welcome to the fourth lecture of Contemporary Math. Today we're going to be talking about chapters 2.3 through 2.5. To start off with, what we're going to start with is set operations. In particular, we're going to be talking about unions and intersections. So, what is a union? A union is this idea of saying, all right, I've got a set, call it A, and I've got a set, call it B. If I want to take the union of A and B, all I'm going to do is say, let's copy everything out of A, and let's copy everything out of B, and put it inside of a new set. And to write this in mathematical notation, what we use is kind of this U-looking shape thing. Don't confuse it with a U, it just kind of looks like a U. I think of it more like a horseshoe because it doesn't have that little hook on the end. So, what does this look like to work with? Well, let's imagine we've got a set A, a set B, and a set C. The set A has elements 1, 2, and lowercase a. The set B has elements lowercase a and lowercase b. Let's say we want to take the union of the two of these. All right, we're going to copy everything out of A, copy everything out of B, and put it inside of a new set. So, the union of set A with set B gives us the element or the set with the elements 1, 2, A, and B. All right, pretty straightforward. Now let's imagine we also have this other set C with the element spoons. If we're going to take the union of A, B, and C, again, we're just copying everything out of A, copying everything out of B, copying everything out of C, and dumping it into the new set. So we're going to end up with 1, 2, A, B, and spoons. That's all there is to unions, really. We're just copying everything out of both the sets and dumping them into a new set. However, talking about intersections, it gets a little bit different. When talking about intersections, we start talking about the shared elements. And this is a really big distinction, right? We're not just saying, let me take everything out of A, let me take everything out of B. Instead, we're saying, take everything that A shares with B. And to write it, what we use is an upside down horseshoe. So it's literally the same symbol, just flipped upside down. So what does this look like in practice? Well, let's keep all of these sets the same. And now let's imagine we also have a set D. The set D is going to have the elements 1, 2, spoons, and B. Now if we wanted to take the intersection between A and D, we would take and find all the shared elements and dump those into a new set. Well, A has 1, 2, and A. B has 1, 2, spoons, and B. So the only shared elements that they have is 1 and 2. So our new set, formed by the intersection of A and D, is going to be the set with the elements 1 and 2. Similarly, the intersection between B and D is going to be the set with the element lowercase b. Now, let's take a moment to pump the brakes a little bit. Let's imagine we were to take the set A and take the intersection with it in the set C. Okay? Notice they don't share anything in common. So what do we write? Well, we just write an empty set. That's all it is. Since they don't have anything in common, the set has no elements. And because the set has no elements, we just write it like this, which is the same thing as writing the empty set. So in the event or in the case where we have nothing in common, we could write the empty set out, or we could just use the notation with that little circle with a line slashed through it. Okay, now, what about the case where we start mixing these up, intersections and unions? Let's imagine for a second, we wanted to take the union of A, B, and C and intersect it with D. All right, we already know that the union of A, B, and C is a set 1, 2, A, B, and spoons. Cool. Now taking that intersection, we're taking that intersection with the set D, which has 1, 2 spoons and B. Notice the only element it doesn't share is A. So we're going to get 1, 2, B, and spoons back. And that's what we got here. Having said that, just as some play, some sense of whether or not you're getting this, why don't we all give this a shot? And if you have any questions about this, send me an email with this particular solution. So what this problem here down at the bottom is, in case you can't see it well, we want to take the union of A and B, and then we want to intersect it with the union of B and D, and then we want to take all of that and union it with C. We want to know what we get back for a set. Like I said, this is just kind of for your own play to see how well you do or don't understand this. If you have any questions about this particular example, shoot me an email, talk about it Monday. Be happy to look over it. Now, before we move on to our next major set operation, namely that of the complement of a set, we first need to talk about what's called the universal set. The universal set can be thought of like a big grab bag of elements that we're going to pull from to make our other sets with. So as an example of this, let's imagine we've got our universal set U. Okay, which I should note, U is usually how we write the universal set. It's usually the notation we use to say this is the universal set. All right, so we've got U, and it has elements 1, 2, 3, 4, A, B, C, D, and E. All right, so we're going to make sets with this. Well, we can make the set A with the elements 1 and 2. We can make the set B with the elements 4, B, C. We can make the set C with the element D in it. Or we can make the set D with the elements 1, 4, A, D, or any other combination of elements that we like. So one way we might write this to help us visualize this is with what's called a Venn diagram. So as you'll see here, we've got ourselves a nice visual depiction of what's going on. We've got the universal set as the big box. Then we've got each of our smaller sets written in a different color as sort of an oval enclosing whatever element we're concerned with. Namely, we start off with our set A with elements 1 and 2 circled, B with 4, B, and C, so forth and so on. And you might be saying to yourself, well, hey, wait a minute. You didn't use elements 3. You didn't use the element E. Yeah, you didn't have to. This is, the universal set is just the possible elements that we can work with. We don't have to work with every element. It's just what we have to construct our sets with. Another way of thinking about this might be, imagine you're a carpenter and you only have one box of screws. You don't want to run to the construction store down the road. You're just stuck with these screws. Well, you might use all of those screws, you might not use all of those screws. But those are the only screws you have to work with. Same idea here. In the same way that that box is the universal set of screws, the universal set is a universal idea of all of the elements you have to work with in this particular case. So, having said that, let's move on to the idea of the complement of the set. What the complement of the set is say, let's say I have a set S. All right, if I want to take its complement, the complement is going to be every element in our universal set that's not in F's. So this is kind of hokey. We're going to see an example in just a second. But before we do, I should point out there's two different ways to denote this. One with an apostrophe and another with a bar over top. Both are equivalent ways of writing this. From what I've seen, the book seems to use the apostrophe. I personally use the bar over top. Both are the same. Having said that, a more formal way of writing the complement of a set would be our complement of our set, however we want to denote it, is equal to the set of all values from our universal set such that they're not in the set. Cool. All right, so let's do this in practice now. Using these same values that we had before, if we wanted to take the complement of the set D, we would say, all right, take all the values, all the elements from the universal set, and remove those elements that are in D. That's the complement of D. So what does that look like? Well, it looks like this. We've got the complement of D is equal to the set with elements 2, 3, B, C, and E. Cool. All right, well, having said this, what about the complement of the union of a bunch of sets? Let's say we take the union of A and B and C and D. We want to take the complement of that. Sure thing, not a problem. We just take everything that's in A, B, C, and D and remove those and say, whatever is left over, that's what we want. So in this particular case, we've got our universal set. We're going to say, all right, scratch off 1 and 2. Cool. We're going to move on to our next set, B. Scratch off 4, B, and C. Cool. 4, B, C. Move on to C. Scratch off D. All right? Move on to D. We've already scratched off 1. Already scratched off 4. Just going to scratch off A. Already scratched off D. What we're left with is the element 3 and E. And that is what the complement's going to be. The complement, then, in this case, of the union of A, B, C, and D is just going to be 3 and E. From here, I'm going to move on to a couple other examples. I'll draw those up on the board really quick and get back to it. So, really quick, going to run through 3 different examples of what all this looks like put together. To start off with, let's consider the universal set of elements pulled from the natural numbers. So the set of natural numbers, those are the numbers like 1, 2, 3, on forever, right? So really, this universal set is just going to be the set of natural numbers. But we're going to use set builder notation to write it out. And if we did, it would look like this. All right, cool. Having said that, then we're going to define 2 different sets, A and B. Set A is going to be the set of values from our universal set such that our values are less than 100. For set B, we're going to pull from, again, the universal set such that our values are going to be greater than 50. Now to write these both out in roster notation, set A would look like the set with elements 1, 2, 3, all the way up through 99. Set B, that would look like the set of elements 51, 52, 53, on forever. Cool. Now, if we were going to take the union of these 2 sets, we can look at the roster notation. We can see, okay, we go 1, 2, 3, 51, 52, up through, we get to 99. Well, set B keeps going on forever. So in roster notation, the union of A and B, it's the numbers 1, 2, 3, on forever. But if we were to take their intersection, because we agree they definitely have numbers in common, from 51 up to 99, right? So if we were to take their intersections, that would be what we would have. We'd have the set with elements from U such that our elements are between 50 and 100. All right, cool. Again, in roster notation, that would look like 51, 52, on and on and on, 98, 99, stop. That would be it. Cool. We draw the next example. For our next example, let's consider we have the universal set with elements 1, 2, 3, 9, 10, 41, 55, 67, 103, and 1,000. And then let's consider we have the sets A and B with elements for A, the elements 1, 2, 3, 9, 10, 41, 55, 67. And for the set B, we have the elements 55, 67, 103, and 1,000. Now, if we wanted to take the intersection between the two, again, we would just be saying, hey, I want the set with the items that are the same, or a set of identical items between the two sets. All right? Well, in this case, 55 and 67 are the only two elements that both A and B share. So, the intersection of A and B is going to be the set with elements 55 and 67. Now to draw all this out as a Venn diagram, we've got our universal set, again with elements 1, 2, 3, 9, 10, 41, 55, 67, 103, and 1,000. And we've got our set A with elements 1, 2, 3, 9, 10, 41, 55, 67. And we've got our set B with elements 55, 67, 103, and 1,000. Notice what both of these structures, these bubbles, enclose, that is our intersection, right? And those items are going to be, those elements are going to be 55, 67. Now I want to make a couple observations here. First, let's say I wanted to take the complement of B. The complement of B would be everything in the universal set that's not in B. So the complement of B in this case would just be 1, 2, 3, 9, 10, 41. Now this isn't exactly A, but it's pretty close to A, right? It's A with whatever's in that intersection removed. In this case, what's in the intersection would be 55 and 67. Cool. And also notice, if I wanted to say, take the union of A and B, and I wanted to know how many elements there were going to be, I might be tempted to say, well, just count them all, everything in A, and count all the elements in B, and add those together. But that's not quite right. Because look what happens. We have that intersection, right? So if we want to know the cardinality of the union of two sets, then we have to say, cool, the cardinality of the union of two sets is cardinality of set 1 plus the cardinality of set 2 minus the cardinality of their intersection. All right, in practice, what this looks like is we've got A, right, with 1, 2, 3, 4, 5, 6, 7, and 8 elements. We've got B with 4 elements. 8 plus 4 would be 12, but we need to subtract that intersection so we don't double count 55 and 67. When we do that, we get 10, which is in fact how many elements you would have taking the union of both of these. And this is really the idea of what we're going to be doing with all of this. This is kind of the whole thought behind sets and set operations. Really quickly, I'm going to show one more example out of the book, and we'll call it a day after that. For our final example, I decided to pull directly out of the book. In particular, it's example 3 on page 100, or at least that's what it is in my instructor's version. So, what the problem states is we're looking at trying to develop a Venn or build a Venn diagram from survey data. In particular, it's a survey of over 60 people about what type of movie genres they like. We have comedy, drama, and science fiction, and again, we're surveying 60 people. Of those 60 people, 6 tell us they like comedy, drama, and science fiction, 13 just comedy, drama, 10 comedy, science fiction, 11 drama, science fiction, 26 just comedy, 21 just drama, 25 just science fiction. So the way we're going to go about this problem is, instead of trying to write down 60 different unique individuals, because that would get cluttered really quickly over here, we're just going to write down the value, the number of people who belong to each of these individual subsets. We're going to do that using this data. We're going to start off by saying, all right, cool, 6 people like comedy, drama, and science fiction. So, looking at this, that would be right there. So we've got 6 people right here. Now, we've got 13 who like just comedy and drama. But of those 13, 6 are going to belong to the comedy, drama, science fiction group. So we're going to have to subtract 6 from 13. All right. 6 from 13 is going to be 7. And that belongs to just the comedy drama section. Cool. From there, we've got 10 who like comedy science fiction, and we need to figure out how many like just comedy and science fiction. So we have to remove those who also like drama. So 6 subtracted from 10, it's going to be 4. And that's going to go, we said comedy science fiction, that is this bubble right here. Again, it's 10 minus 6. Now, drama, science fiction, but we have to remove those who like comedy to get just those who only like drama and science fiction. 6 subtracted from 11 is going to be 5. Goes into this nice little bubble right here. All right. Now things get a little bit more cattywampus on us. We've got 26 people who like comedy, 26 on a whole. But we want to be able to figure out how many like only just comedy. Well, if we know that 26 people on a whole like comedy, we can use what likes the others to figure out what likes this. And we can do that by saying, let's add these up. All right? 4 plus 6, 10. 10 plus 7, 17. We're going to subtract 17 from this 26. And we're going to be left with just 9. Cool. Makes sense. 17 plus 9, 26. And that's how many people belong in just the comedy circle alone. Now, we're gonna do the same thing with drama. 21 people like drama. All right, so we've got 18 who like all the other genres and drama. So we're going to subtract 18 from 21, just 3. And we're going to do the same thing with 25. Oh, we got 15. 15 minus 25. Or I mean 25 minus 15. So we're going to do 10. And from here, we still have to do one last thing. We have to make sure that we've accounted for everyone. If we're missing anyone out of here, we need to put them out here. So, adding everything up, we've got 10, 20, 30, 30 plus 9, 39, 44. All right, 44 people like comedy, drama, and or science fiction. Well, we started off with 16, so we have to subtract, we started off with 60, so we have to subtract 44 from 60. We're gonna end up with 16 people. 16 people unaccounted for in all of these other situations. Now, having gone through this example, if y'all have any questions, because I know this can be a little foggy, by all means, please feel free to shoot me an email. In the meantime, otherwise, see you on Monday.